Algebraic rules of reflections and rotations. Our do now reads, the graph below shows the relationship between x, the number of movie tickets purchased, and y, the total cost of the tickets. What does point P represent on the graph? So we have point P right here. And as you can see, point P represents 6 tickets for $30. So the price of one ticket is not $30, so we can cross out A and B. And so C and D both have the price of 6 tickets is $30. The only difference is that C is saying that it's $5 per ticket, and D is saying that it's $6 per ticket. So there's 2 ways that you can do this. The first way is just identifying point 1, comma, its X value is 1, so that's the number of movie tickets, and so its Y value is 5, so that shows us that it's $5 per ticket. Another way of solving this is using our constant of proportionality equation. So we have K is equal to Y over X. So 6 is our X coordinate, 30 is our Y coordinate. So if we plug in the numbers into the equation, we have 30 over 6, or 30 divided by 6, and that is 5. Our TEK is 8.10c. Again, we will explain the effects of reflections and rotations on two-dimensional shapes on a coordinate plane using an algebraic representation. Some vocabulary words that we've been going through all week. Congruence means same shape and same size. Picture to the right is a coordinate plane and some images. And something to point out is that the pre-image, or the original image, is going to be this blue triangle. So anytime it's like A, comma, B, comma, C, comma, what looks like that, that shows a transformation. The original figure, or the pre-image, does not have that little comma next to the letter. Points or shapes can be reflected across the x-axis, the y-axis, or a line. Orientation means the direction that the point or the figure is facing. And as a reminder, rotations happen in 90-degree intervals. So the first rotation is 90 degrees, and it can either be rotated clockwise or counterclockwise. We'll get into that a little bit later. 180 degrees, 270 degrees, or 360 degrees. And 360 degrees just means that it's back in its original position. So if this was our original shape, it's our pre-image. If it were to go counterclockwise, it would go the opposite way that a clock goes. And so that's from right to left. And then if it were to go clockwise, it's moving from left to right, which is the way that a normal analog clock would go. And so whether a shape or a point is rotated clockwise or counterclockwise is very important to pay attention to, because that will change the different rules that applies to the points of the shape rotating. And lastly, the 4 different transformations that we've been going over all week include translation, which we went over yesterday with moving the shape across a coordinate plane, so changing its x coordinate and then changing its y coordinate. Reflection, which we also went over a little bit. rotation, which we're going to go into more detail today about, and dilation, which is the first transformation that we really learned about. So for a reflection flips a figure across or over a line, and each point of the new figure is equally distant from the line of reflection. Reflected figures have the same size and shape, so they maintain congruence, but different orientation. They do change the direction that they're facing. And imagine that reflection is like looking into a mirror or your left and your right hands. They look about the same shape and the same size, but they're facing opposite directions. As you can see, my thumbs are pointing in opposite ways. So when a point is reflected across the x or y axis, one coordinate remains the same while the other changes to its opposite. So now we're going to explore an example and the rules. So I'm going to draw a coordinate plane. So let's say we have the point 3, 2, which is something like this. If it were to be reflected across the x-axis, which is this point right here, or not point, but it's this line right here, it would look something like this. So as you can see, the x-coordinate for both is still 3. It's the y-coordinate that changes signs. So up here, the y-coordinate was positive 2, and now after it's been reflected across the x-axis, the y-coordinate is negative 2. So the algebraic rule is x comma y to x comma negative y. I'm going to draw another coordinate plane. This one's not so straight. And let's say we have that same point, 3, 2. If it's reflected across the y-axis, this is our y-axis right here. And our reflected point would look something like this. So if this original point, the pre-image point, was 3, 2, our x-coordinate has changed. Its value is the opposite, right? So from 3, positive 3, it becomes negative 3. The y-coordinate remains the same. So something to remember is that the opposite applies. So if you're reflecting a point across the x-axis, it's the y-coordinate, not the x-coordinate, it's the y-coordinate that changes its sign. And let's say we had 3, negative 2 instead of 3, positive 2. If it were to be reflected across the x-axis, it would become 3, positive 2, because negative 2, two negatives right next to each other become a positive. Okay, and then for a reflection across the y-axis, the y-coordinate is not changing signs, it's the x-coordinate that's changing signs. So the x-coordinate that was once positive now becomes negative. Okay, moving on to rotations. Rotations is a little bit more complex because the rules depend on whether you're moving clockwise or counterclockwise. So a rotation turns a shape as if it were attached to a wheel, right? And so let's say we have a coordinate plane. Let me draw it. Okay, we have the example 3, 2. So 3, 2, again, is somewhere along there. If it were to rotate counterclockwise, 0 degrees or 360 degrees, it would end up at the exact same place. So the example is 3, 2, rotating 0 or 360 degrees is 3, 2. That's where the new point would end up. And so the algebraic rule to represent that is x, y to x, y. Then for the 90 degrees rotation counterclockwise, we have our point 3, 2, and then our new point is going to be negative 2, 3. So as you can see, the x and the y coordinates switch places. So the number that was once 3 becomes the number that's 2. The number that was once 2 becomes 3. They just switch places. And also, If it's rotating counterclockwise, then it's the x coordinate that changes because it went from being positive to now negative. So the x coordinate changes, but the y coordinate keeps the sign. Then let's say that we're rotating this 3, 2, 180 degrees. This would be the new point. So we have -3, -2. The 180-degree rotation is pretty easy to remember because you're just changing the signs of both numbers. You keep both numbers as they are, you change the sign. So if they were both positive, you change them to negative. If they were both negative, you change them to positive. If one of them was positive, you change it to negative, vice versa. The 270 can also be a little bit confusing because again, you're flipping around the x and the y coordinate. I think it should be a little bit lower, but bear with me, it's going to be an extra big dot. So not only do we change the x and the y, but now it's the y, or it's the x coordinate that you have to change the sign of. So when originally the point was 3, 2, now the point is 2, -3, because what was once the x coordinate now is in the y coordinate position, but it changes its sign. And then on top of that, if you rotate it clockwise, this rule right here, I'm going to demonstrate it. I'm going to draw another coordinate plane. Imagine that these are straight lines, of course. We have 3, 2, and if it were to rotate 90 degrees clockwise, so if we have 3, 2, we're going to flip our x and our y, so it's going to be 2, -3, right? Because our x coordinate, it's still going to be positive, but it's our y coordinate that's negative now. So these are a lot of rules to try to remember. 90 and 270 are going to be the ones that are confusing because not only are you changing the signs, whether it's positive or negative, but you're changing the order of the numbers. And then you have to figure out if it's counterclockwise, are we changing the sign of the x or the y? If it's clockwise, are we changing the sign of the x or the y? But hopefully a few examples will allow you to practice these rules and see how they work. For this first I do, the problem reads, look at rectangle RSTU and its transformation. Write an algebraic rule to describe the transformation. So the first thing that I'm going to do is to identify the pre-image. The pre-image is going to be this blue rectangle because as you can see, there's no little comma next to the letters. And I see that it's reflected because it's the same unit away from this y-axis. So it's reflected across the y-axis. So I'm going to start by writing my rule as x, y. 2, so I can see that it's my y values that are flipped in sign, so it's going to be -x, y. And just as a reminder, when points are reflected across the y-axis, it's the x-axis that changes signs. Just to show what that looks like with a point, let's choose R. Point R's coordinates are -4, -1. And then reflected R's point is +4, -1. So using this rule, our original pre-image point was -4, 1. Then after its reflection across the y-axis, it becomes +4. So if we had input the -4 here, it'd be -4, because x was originally -4, and then we're putting a negative in front of it. 2 negatives make a positive, so +4, -1. Sorry, this was also supposed to be -1. So the original point was actually -4, -1, not +1. And then the reflected point was +4, -1. To answer the question in this box, does the figure preserve congruence? Yes, it preserves congruence because the shape, even after it's been reflected, is the same shape, same size. And does the figure preserve orientation? No, it does not. Because even though the rectangle, the pre-image rectangle looks pretty much the same as the reflected rectangle, if you look, R that was once in the upper left-hand corner facing the left is now in the upper right-hand corner facing the right, or it's on the right side is what I mean. And in the original R, it was on the left side. So it does not preserve the direction that it's facing. For this I do, it says we have to write an algebraic rule for this transformation. I can obviously see that it's a rotation. And so I'm first going to identify what the pre-image is, which is this blue quadrilateral. And so I can see that it's been rotated clockwise by 90 degrees. So I'm going to start by trying to write my rule. X comma y 2. So I know that I'm going to have to flip my x and my y around, but I know that one of the signs is going to be flipped as well. So let's look at this. So the x values here used to be negative, and now they're all positive. So it's probably going to be my x values, what is now my x value, which is the number of the y value. So to show what that means, let's choose this point A. The coordinate for A is -4, 2. And then the point of reflected A is 2, 4. So as you can see from the original point to the reflected point, we switch the numbers around, and what was once a negative number becomes a positive number. So over here, we have -4, 2. We flip the numbers around, so we have 2, oh, I was right the first time. See, that's why we don't second guess ourselves, because we're usually right the first time. So we have 2, because our y value now becomes our x value, and then a -4 is the same thing as a +4. So then we have 2, 4, and that's how we got our reflected point 90 degrees clockwise. If it were to be counterclockwise, then the rule would be switched. So it would be the negative y, positive x. And that's why it can be confusing, because it depends on which direction you're rotating it 90 degrees. So the rule for rotating it 90 degrees clockwise is going to be x, y to y, -x. But the rule for counterclockwise, rotating it 90 degrees counterclockwise, is x, y to -y, x. There was some we do problems and then some you do problems, and finally your 4-question Google form DOL. Thank you so much for following along in today's math lesson, and see you in the next math video.